Okay, let's dive right into this explainer. Have you ever looked up at the night sky, spotted a faint, kind of glowing smudge, and wondered, just how long have those exact pinpricks of light been burning out there in the dark? It's a pretty fundamental question in astronomy, but, the answer is rarely simple. Today, we're going to embark on a cosmic detective story to unravel that very mystery for one specific, absolutely fascinating target. We'll be walking step by step through the incredible forensic methods scientists actually use to crack the case.
So let me ask you this right out of the gate. How exactly do we look at distant points of light and figure out how old they are? I mean, down here on Earth, our dating methods are fairly hands-on, right? We can carbon date ancient artifacts, or we can literally just count the rings of an old tree to know exactly how long it's been standing. But in space, we can't exactly walk up to a star with a thermometer and take a core sample. We have to rely entirely on the light traveling across the vast empty void and use some incredibly clever physics to decode the story that light carries.
To really wrap our heads around the scale of this mystery, we have to look across 3,600 light-years of space. That is the staggering distance to our prime suspect today, Caldwell 71. To put that into perspective, the light we are analyzing from this cluster today, the literal photons hitting our telescope lenses right now, they actually began their journey to Earth 3,600 years ago. We are quite literally looking back in time, catching ancient light to piece together this giant galactic puzzle.
So here is the roadmap for a forensic investigation into the cosmos today. 1. Meet the termite hole. 2. The cosmic dust screen. 3. Clues from cooling embers. 4. The ringing stars. And 5. The final age verdict. Let's get into it.
Section 1. Meet the termite hole, the scene of the crime.
Now, what's really wild about this suspect is that this massive gathering of stars in the Milky Way has been watched by astronomers for centuries, yet its exact age has remained this really stubborn mystery. Caldwell 71, which you might also hear called NGC 2477 or the Termite Hole Cluster, is a densely packed open cluster residing right in the Puppis constellation. It was actually discovered way back in 1751 by Abbé Nicolas Louis de Lacaille during an expedition to South Africa. You'd think, right, with hundreds of years of observation, we'd know absolutely everything about the whole shebang, but pinning down the exact timeline of its birth has been a major scientific hurdle, and a lot of that comes down to exactly where it's located in the sky.
Section 2. The cosmic dust screen obscuring the truth. Because, hey, every good mystery has an obstacle. Take a look at these heat maps. They brilliantly illustrate the dense, cosmic dust that astronomers have to computationally wipe away just to see the true stars hidden behind. You see, space isn't perfectly empty. It's actually filled with swirling, irregular clouds of gas and dust. It's almost like a chaotic cosmic weather system. Caldwell 71 is situated in a region of the Milky Way where intervening interstellar dust absorbs and scatters the starlight heading our way. Astronomers call this differential reddening because the dust isn't just a uniform flat sheet, it's extremely patchy. It makes some stars look redder and fainter than others in highly irregular ways, which completely skews our data. To fix this, scientists have to use advanced 2D dust maps and precise data from the Gaia satellite to calculate and digitally remove this background extinction. Only by clearing this cosmic smoke can we get a true reading on the star's actual brightness and temperature.
Section 3. Clues from cooling embers, the white dwarf method.
So, once that dust is finally cleared away, what tools do we use? Well, think of this color magnitude diagram as basically a fingerprint at a crime scene. See region 4? That highlights our cooling embers, white dwarf stars whose fading temperatures tell us exactly how long ago their stellar fires died out. Using incredibly deep photometric observations from the Hubble Space Telescope, astronomers isolated these faint stellar remnants. A white dwarf is essentially the incredibly dense core left behind after a medium-sized star burns up all of its nuclear fuel. Because they aren't generating new energy through active fusion anymore, they don't make new heat. They simply cool down over time at a very steady, highly predictable rate in the freezing vacuum of space. By measuring just how cold and dim these specific white dwarfs in region 4 have become, astronomers calculated a timeline. Using this cooling sequence, researchers determined an age for the cluster of roughly 1.035 billion years. But, in rigorous science, one method is never quite enough. We always want independent verification.
Section 4. The ringing stars, astroseismology. Let's see how a totally different method builds our case.
Instead of looking at dead embers, astroseismology is kind of like listening to ringing bells. The frequency of a star's physical oscillation tells us its exact internal structure and its age. While white dwarf cooling relies on the fading heat of dead remnants, Astroseismology looks at living, active stars. Here's the thing. Stars are not just static, silent spheres of gas. They actually pulsate. Sound waves bounce around inside them, causing their starlight to slightly fluctuate over time. The speed, intensity, and frequency of these acoustic waves depend directly on the star's internal density and chemical makeup. And because a star's core fundamentally changes as it ages and burns through its hydrogen supply, those internal notes shift. By capturing that rhythm, we can effectively read a star's age from the inside out. It is a literal game changer.
And thanks to the brilliant data from the TESS satellite, astronomers successfully pinpointed 16 specific, uncontaminated ringing stars within this very cluster to test against stellar revolution codes. The TESS satellite is uniquely suited for this because it captures high-precision photometry by just staring at patches of the sky, measuring those tiny rhythmic dips and spikes in starlight. But remember, the center of Caldwell 71 is packed tightly with stars. To avoid blending the light of multiple stars together, which would completely ruin the delicate data, scientists used a specialized tool called TESSIPAC. This let them draw custom visual apertures and isolate exactly 16 uncontaminated pulsating stars. By running these clear, ringing frequencies through advanced computer modeling software like MESA and GEAR, they can match the observed rhythmic notes to theoretical stellar models, giving us a completely independent, highly precise age calculation for the cluster.
Section 5. The final age verdict, synthesizing the data. Time for the grand finale. It is incredibly thrilling to see how data from all these sources beautifully align, giving us a highly confident verdict that the termite hole cluster is about 1 billion years old. Let's look at the A-team we've assembled here. We have the Hubble Space Telescope providing deep insights for the white dwarf cooling sequence. We've got the Gaia satellite providing precise proper motion data to confirm exactly which stars belong to the cluster while mapping that obscuring dust. We have the TESS satellite measuring the internal astrosismic ringing of the living stars. And we have advanced isochrone fitting models, specifically Parsec and MIST, overlaying theoretical evolutionary tracks onto all of this cleaned data. Separately, these are powerful tools, but together, they converge on a single unified timeline, independently locking in the cluster's age at approximately 1 billion years old with remarkable precision.
As we wrap up this explainer, I want to leave you with this provocative thought about what future cosmic detectives might uncover when they look at this exact same patch of the Puppis constellation. If Caldwell 71 is 1 billion years old today, what will its stars tell us a billion years from now? How many of those brightly ringing stars we just measured will have faded into quiet, cooling embers, waiting for an entirely new generation of astronomers to decode their secrets? It's a profound reminder that the universe is incredibly dynamic, ever-changing, and always waiting to be understood.